So circles and chords. Circles and chords. So we have a circle. Circle is basically the set of points that are equidistant from one point. So if you took a point and you tied a string to a pencil and you moved it around, all of those points are the same exact distance away. It's what you do when you draw a circle with your compass, right? It's just a set of points. You don't move the center, so all of those points are the same exact distance away, that distance being the radius. And so the first thing we're going to talk about is this term chord. If a line intersects the interior of a circle, then it contains a chord of the circle. All right, and so one of the chords that we just used was the diameter. That is a chord that goes through the center. But anything that cuts through the circle, meaning the interior of the circle has the line going through it, is a chord. So this line LM is a chord of this circle. This line QR is a chord of this circle. All right, so those are considered chords. The next thing they tell us here is that if a radius is perpendicular to the chord, then it bisects the chord. And so if you have a radius that is perpendicular to the chord, then we know that it bisects the chord. All right. And so then they give us a little bit more information down here. If a radius bisects a chord that is not a diameter, then it is perpendicular to the chord. It's kind of the converse of what we just said. The line in a plane of a circle that is perpendicular to the bisector of chord contains the center of the circle. So if it's going to bisect a chord, it's going to contain the center. And so let's look at this picture right here. What the theorem is telling us is that if the radius is perpendicular to the chord, then it bisects it, and vice versa. If it bisects the chord, then it's going to be perpendicular to it. Okay? So basically, the radius becomes a perpendicular bisector of a chord. All right? And so those two things are true. If the radius is perpendicular to this chord, then it bisects it, meaning these two little pieces are the same. Or if you know the two pieces are the same, you can assume that it is perpendicular. All right? So it says find the diameter. It wants the diameter here. Let's look at what they gave us. It says OD. So from here to here, it's not quite the radius, it's part of it, is 3 inches. And AB is 8 inches. AB is 8 inches. All right. So all the way here is 8 inches. All right. So they've given us 2 pieces of information. We know that, I'm going to make this guy a little bit bigger so that you can see it. We know that because it's perpendicular, these 2 pieces are congruent. And they gave us the entire amount of 8, which means each individual piece is 4. So we know that those individual pieces there are 4. And then they told us that from A to D is 3 inches. We have what type of triangle there? What type of triangle is this when you see it out, if I were to pull it out? It's a right triangle. And how do we know that? We have notation there, right? Right there. So if they want to know the radius, which piece of this is the radius? Well, this is a radius right here, and this is a radius right here, which is also what piece of the right triangle? My radius is what piece of the right triangle? The hypotenuse, all right? So how do I find the hypotenuse of a right triangle if I know the 2 legs? Pythagorean theorem, which this is a Pythagorean triple, so we actually, it's 3, 4, we already know it's 5. But if you don't, 3 squared plus 4 squared equals my radius there, squared. 9 plus 16, 25. Square root of 25 is 5. So when I'm finding the radius here, I know the radius is 5 inches. What did they ask for? The diameter. So I'm not quite done. What do I need to do to this radius? I need to double it. So my diameter here is going to be 10 inches. So knowing that your radius is perpendicular and that it bisects can help you find different pieces of this circle. If you know that, then you can find different pieces of the circle. All right, let's look at a couple more theorems here. Incongruent circles, or in the same circle. 2 chords are congruent if and only if they are equidistant from the center. Equidistant means the same distance, okay? So if I want to know whether QR is congruent to PN, I need to know, are they the same distance from the center? So I need to know, is A to X the same length as B to Y? Those are two different circles, two congruent circles. It would work in the same circle as well. So if I wanted to have another chord in the same circle here, I could actually use the same process or the same thinking as long as this guy's perpendicular from the radius here. I could do it here as well. If I wanted to know if XY is congruent to QX there, then I would need to know, is AX congruent to AZ? If they are the same distance from the circle, those chords are going to be the same length. That's what this theorem is telling us. If they are the same distance from the center, they are the same length. They must be. All right? So let's look at example 2 here. All right. Find AB and GF. If CD, HI are congruent, CE equals HJ, AB is 5y minus 3, GF is 2y plus 9. So when you're given something like this, you want to see exactly what they've given you, all right? So you want to see exactly what they've given you. They are telling us that CD is congruent to HI. What did they tell us about those two circles? If the radius is congruent, what can we assume about the entire circle? They're congruent. You can't draw two circles with the same size radius and they not be congruent circles, by definition. Yeah, it's defined by the radius. So if the radius is 4 inches and the other radius is 4 inches, those circles are going to be identical. They're going to be congruent, all right? So by telling us that information, really all they said is you have congruent circles. Because in order to use this theorem, you have to know that, all right? Let's see what else they told us. They said that CE is congruent to HJ. All right, so why is this important? Well, this is important because we know those are the same distance. So C to E is congruent to H to J. If I can move this back here, all right, is H to J. So I know that these two lines here, this line and that line are congruent, which tells me that those chords are the same distance away from those circle centers, okay? They're the same distance away. Then they're telling me that AB, so A to B is this, and G to F is that. By the previous information, I know those two are congruent, all right? So if I want to solve for y, I can just set them equal to each other because all the information leading up to that was just getting me to the point of saying, oh, I know they're congruent. Now that I know they're congruent, I can set them equal to each other. So I can just say 5y minus 3 equals 2y plus 9. All right? How do I solve this? Cade, what's my first step? Solving this. Yeah, combine like terms. So I want all of my variables on one side and all my numbers on the other. My like terms here are my 5y and my 2y. I want them on one side. My constants are my -3 and my 9. So I want those on another side. So I'm going to subtract my 2y over to this side. And I'm going to add my 3 to the other side. And so on the left-hand side, my 3's have canceled. And I have 5y minus 2y's. Maggie, how many y's do I have? 5 minus 2. Yep. And then over here, these cancel. I have 9 and 12 on this particular side. Emmy, 9 plus 12. My 9 plus 3, what do I have there?
You have 12.
Yep. All right. And what's my final step here, Malia?
Divide by 3.
Divide by 3. So what is my y? Y equals what? 4. All right. Am I done? No. What did they ask for? What was the initial question in all of this? Yeah, find the links, and they gave me 2 of these, right? They gave me A, B, and G, F, right? A, B, and G, F. So if I want to solve for A, B, Faith, what am I going to do with that Y right here? What do I need to do with that 4? plug it in, right? So I'm going to plug it in. So if I want to solve for AB, I'm going to plug that 4 in. And I'm going to say 5 times 4 minus 3. 20 minus 3. What do I get for AB? 17. Same thing for GF. If I want to solve for GF, I'm going to plug it in. GF is going to be 2 times 4 plus 9. 8 and 9 give me what for GF? Also 17. That makes sense. Why does that make sense? I established at the very beginning that if they're the same distance away, they are the same length. So actually, once I solved for one, I didn't have to plug it in. I would recommend you do that because if you got a different answer, then maybe that would clue you in that you did something wrong if you knew they were supposed to be equal. All right? Questions on that one? All right, find CH and HB. If AD equals GE, which equals 10 centimeters. All right, which equals 10 centimeters. So they want me to find CH and HB. So basically they want me to find the two pieces of this guy. We know that AD and GE equal 10. All right, so let's start with what we know. We know that this is 10 and this is 10, which means they're the same length, right? Which also tells me that from the center is the same length, right? That's the converse of what we just did. They told us they're the same length, so now we can assume they're the same distance from the center, all right? We also know what the length is. The length is 10, all right? The length is 10, okay? So if we know the length is 10, we know that it bisects that guy. So if the entire length is 10, these two are the same, or all four of those rather are the same. So that means these are going to be 5, right? Does that make sense? Those are 5, okay? Right? Okay. And they gave me this little piece of information right here, which is somewhat important if I'm solving this. 13. All right? Because 13 is the hypotenuse of a right triangle. So I have this right triangle here. If I were to do this one, so this is C, J, and E. I'll just pull that one out. We just established that this part's 5. They told us this part's 13. How do I find from C to J? How do I find from C to J? What's my theorem? We've used it about 1,000 times. Pythagorean theorem. So I'm going to say a squared, which I don't know, plus b squared, which is 5, equals c squared, which is 13. All right? A squared plus 25. 13 squared is 169. Okay? A squared. Subtract 25 over. We're going to get what? Hopefully that. So what is a? Square root of 144. What is it? 12. All right? So I know this guy is 12. They actually didn't ask for him. They asked for CH. But what do I know about CJ and CH? They are the same. So I know that if CJ equals 12, then I also know that CH equals 12. So I've actually solved for that one. Now, how do I solve for the other little tiny piece? What is from C all the way down to F? Well, you gave me the answer. What is this guy? 13. How do I know that? It's a what? It's a radius. Kai, what do I know about the radius then? If I know this one? They're all the same. So if I know from C to E, the center to a point is 13, then C to F should be 13, and C to B should be 13, and any other radius that I draw should be 13. All the radii are 13, okay? So if I know from C to J is 12, and C all the way to F is 13, what's the little piece left over? 1, which means this little piece left over, which is what I'm actually solving for, is also 1. H to B is also going to be equal to 1. All right, questions on that? So flip to page 348. There's a whole bunch of information here. I want you to do all of these, 10 to 19. Some of these require absolutely no solving whatsoever. They are literally just figuring out if it's the same as something else they've already given you. All right? So take about 5 or 6 minutes and do those. Find AH if AD is 4. All right. Find AH if AD is 4. Those are both what of that circle? Those are both the radius, so they should be equal to the same thing. You should have gotten 4 there. Find BC if BE is 18. Find BC if BE is 18. We know this is perpendicular, so we know it bisects it. So if the whole thing is 18, you should have cut it in half. You should have gotten 9 there. It bisects it. Find FI if AG and AC are congruent. So these two are equidistant. And BE is 12. If these two are the same distance away, we know they are the same. You didn't have to do any math there. They're just the same, 12. Find AG. That's this one right here. If FI is 16, BE is 16, and AC is 6. They just told us these were the same length, which means these are the same distance. All right? So again, you didn't have to do anything. You just had to figure out they were the same. That is 6 as well. If these are the same distance away, if these are the same length, then that means they're the same distance away from the center. So they told you these were the same length, and they told you this distance. So this distance must be the same. All right. Find BE, which is this chord right here. If AG and AC are congruent, and I to G is 10. Well, if these are congruent, that means B to E and I to F are the same. They gave you half of this, so you should have just doubled it, but it then would have been the same length as BE, 20. 20. All right. Next one, find AI. That's actually from here to here, all right? So that's a radius. If AC and AG are congruent, BE is 10 and AC is 4. So for this one, they basically told us this is 4 because we know they're congruent. This entire length BE is 10, which means that this piece, these are cut in half. This would be 5, 4, 5, right? So what did we have to use there? What theorem? Pythagorean theorem. So 5 squared plus 4 squared equals what we're trying to find squared. 25 plus 16. You should have gotten the square root of 41. If you put it into your calculator, you would have gotten approximately 6.4. So approximately 6.4 there if you did it in your calculator. All right. Find AB if AC is 4 and BE is 6. So AC is 4, BE is 6, which would cut it in half. So you should have done 3, 4, and then Pythagorean theorem would have given you 5. Find HF if GH is 6, which is this piece right here, and then I to G is 12. So you could have assumed that those were as well, and you could have again done Pythagorean theorem. If you put it in your calculator, 6 squared of 5 is approximately 13.4 there. All right, find AG. If they told you these two are congruent, so they're just telling you the same distance away. BC is 4 and A to B is 7. So again, Pythagorean theorem, square root of 33, that's approximately 5.7. And then find F to I. F to I, if AI is 8, that's your hypotenuse, and AG is 6. Pythagorean theorem, you should have subtracted. That would have given you half of it and then doubled it. If you did that in your calculator, you would have gotten approximately 10.6. Two terms here. A secant intersects a circle at 2 points. So this line MN is a secant. All right, tangent. It means to touch, by the way, because it only touches, in contrast to the secant, which crosses through it twice, the tangent intersects it at exactly 1 point. So this line DG here would be a tangent. Secant crosses it twice here. A tangent touches it, means it touches it or crosses it once. Crosses it once, all right? Let's talk about some theorems about tangents. A tangent is by definition is a line in the same plane as a circle that intersects the circle in exactly one point, called the point of tangency. The theorem here is if a line is tangent to a circle, then it is perpendicular to the radius that is drawn at that point of tangency. So this means if AB is tangent, then it is going to be perpendicular to this radius OA. All right, it's going to be perpendicular. What this does is we can then create this right triangle here and solve for some information with our tangent lines. If we know it's tangent and we have a radius touching it, we know they're perpendicular. So it creates this right triangle, which again, you're going to use Pythagorean theorem. So it wants us to find the measure of the angle if these are tangent. All right, so first of all, we know a couple things. We know that this is what type of figure. If I were to just take this entire thing, how many sides do we have here? 1, 2, 3, and 4. All right. How many? What's the angle measure of a four-sided figure inside? 360, right? 4 minus 2, right? Times 180, right? We know that from our theorem a while back. So all of these add up to 360. All right. We know two of them. This is going to be what? These are both going to be what? Right angles, because it's tangent lines. So I know that I have 180 degrees accounted for. And I need to add the other two, x and 3x. Right? So what do I do here? Subtract my 180. I'm going to get 4x equals 180. My last step's to do what? Divide by 4. X equals 45. So I know angle A is 45. How do I solve for angle C? What do I do with that guy? Multiply by 3. So 45 times 3. All right. So knowing that it's perpendicular, you can use that with your angles, and you can use that to calculate as well. All right. Look at one more theorem here. Top of page 353. Top of page 353. This is an important one as well. Tangent segments from an exterior point are congruent. Here's my exterior point. These are both tangents to this same circle. So that means that A to X is the same length as B to X. A to X is the same length as B to X. All right. That means you can set them equal to each other if you had variables involved. That also means if you look at example 2, perimeter. Q to W should be the same as Q to X. Q to W should be the same as Q to X. R to X should be the same as R to Y. You can work it all the way around. S to Y is the same as S to Z. P to W is the same as P to Z. These are all tangent lines. So if they wanted the perimeter, you could just add them all up because you know that those pieces are congruent to each other. All right. So I have a little bit of a handout here. We're going to fill in some stuff with this. We're only going to fill out part of it. The other part we're going to finish as we get to it. Some terms that we've learned so far. Circle is the first term. Set of all points that are the same distance from the center. A radius is the segment from the center to a point on the circle. A chord, line segments whose endpoints are on the circle. And a diameter specifically is a chord that passes through the center of the circle. Page. A secant is a line that intersects the circle twice. A tangent line is a line that touches the circle once, and the point of tangency is the point where that tangent touches the line. We are going to get to these so you can go and fill them in. An arc is a piece of the circumference, and a sector is a piece of the area of the circle. We worked with them a little bit in the last chapter. We did not talk about minor, major, and semicircle. Minor's less than 180, major's more than 180, semicircle is exactly 180. And we will get to those in the next couple of sections. So you can go ahead and fill those in. The properties that we have talked about with the tangents. Tangent and radius. If a tangent and a radius or diameter meet, they are perpendicular. If a tangent and a radius meet, they are perpendicular. In order for that to be a tangent line, that has to be a right triangle. If it's not a right triangle, you don't have a tangent line. Which means if they want us to solve for x here, they've given us 5 and 12. 5 and 12. You are going to use Pythagorean theorem. 12 squared plus 5 squared equals x squared. Which means 144 plus 25 equals x squared. Which means it's the square root of 169. So x here is 13. That is the only way that's a tangent line. If that does not work, that's not a tangent line. So if they gave me all 3 of the sides and said, is it tangent? You would use Pythagorean theorem to prove it is or isn't. If they gave you 2 of the sides and told you it was tangent and wanted the third side, you would use Pythagorean theorem to solve for the third side. All right, if it is tangent, it will be perpendicular to a radius or diameter that touches it. And then the second one we talked about, 2 tangents. If 2 tangents meet at the same exterior point, the segments are equal. So those are 2 tangents. That means 3x plus 10 will equal 2x plus 5, because I know that if I want to solve for x, I can set them equal to each other and solve. If they wanted one of the lengths, I would plug it back in and solve for one of the lengths.